Hey,
Hi.
Did you all get time to read the probability chapter?
Yeah. But I
What about,
myself have a lot
yeah,
of questions.
okay. Yeah, like what about exercises? Like, are we going to solve some exercises today?
I
Should
actually
we
did
go?
not get the time to look for exercises. So
Yeah, sure, sure.
maybe I don't have anything right now.
I have a I have a reference called I think the book's author's name is Ross.
Uh,
Uh, First Course in Probability, Sheldon Ross. This is like the book which we referred in undergrad for probability. It's really good, and it has a lot of exercises as well for each topic.
okay. I think let's wait for a minute or two and then shall we get started?
Yes, yes.
Okay. I'm just guessing if Andrea might join, that's why. Yeah.
Yeah, yeah.
Okay, I think I'll get started while others can join during the presentation. Sharing my screen right now. Okay. Um, Okay, so last time we were done with the conditional probability and the chain rule of probabilities, right? So no questions over here, right? We're good until here. So I'll move on to the next topic, which is independence and conditional independence. This is again straightforward. It's assuming independence of probability. So the occurrence of one distribution does not affect the probability distribution of another random variable. So here in that case, we can actually express the probability, like the joint probability distribution in terms of two factors. And it is denoted by the symbol, which is the symbol for independence. And in the same way, we have conditional independence, where given another random variable z, the distributions of x and y are conditionally independent. So the formula comes down to this, where they are still expressed as products of the two factors, but they are conditioned on the occurrence of the distribution of z. That's the difference. And it's denoted by this like the term where you have the independence and then it's conditioned on the z term. Next, we have expectation. So expected value is actually asking the question, say you draw a random sample from a probability distribution, what do you expect that to be on an average? So here the expected value is more like a generalization of the idea of a mean value, but it might not always be the value that centers the distribution. Also here, the formula for this is the function times the probability distribution, and you're summing over it. So I just want to show an example of this. So here we have expected value of f of x. So if we take samples from the distribution, right, and we have the function for that, it will be f of x1 probability of x1 plus f of x2 probability of probability of x2, and so on. So this is the formula for expected value. So to give you an example, let's say, let's ask the question, what is the, so before that, let me give you the data. So say we have rolled a dice, and the rolls are 1, 2, 3, 4, 5, 6. And then we have probabilities for it, which is all 1 by 6, right? Because equally likely to get any one of the numbers. And let's say the function here that we want to see is, say if the roll is x and this is p of x, say we want to square it. So the function here is a square function. So 1, 4, 9, 16, 25, and 36. And why are we taking this is, so in this example, say a friend of yours tells you that I'll give you this amount for each of the dice rolls. If you roll a 6, you'll get you'll get $36. If you roll a 5, you'll get $25, and so on. So the question to ask here is, what is the fair price to play the game? Is it worth it to play the game? And if I play the game, what is the fair price that I would get? And based on that, to make a judgment whether to play the game, and will I be able to get a good amount for it? So this is where expected value comes in. So you want to find the, on an average, what is the value that you're going to get for this? So here, according to the formula, we write expected value of f of x square. And then here it is the function times the probability, right? So 1 times 1 by 6 plus 4 times 1 by 6 plus 9 times 1 by 6 plus 25 times 1 by 6 plus 36 times 1 by 6. This is how we calculate it. And it will give you 91 by 6, which is somewhere between 9 and 16. So over here. So when you play this game, on an average, you might get a value, like you might be earning between 9 and 16. So that's the expected value. And expected value has some properties, which is, it is linear. So linearity, linearity means, so if L is some function, right? Goes from Rm to Rn, real values. So what linearity is it can be additive, and then if it is a product of some value, scalar, then the scalar comes out. So this is the general linearity. So expected value is also linear. So say you have f of like f1 of x, f2 of x, and so on. You can decompose them into sum of expectations. Oh, sorry. different functions. And so on, expectation of fn of x. And also in this case, say you have expectation of alpha f1 of x. Then you can bring out the scalar, and then it becomes expectation of f1 of x. So this is a linearity property, and expectation is linear. So after this, we have variance and standard deviation. So we have expectation, which is kind of like a mean value, right? But expectation alone cannot tell us anything about the distribution. It will just tell you, okay, where it lies at the center maybe, but it doesn't tell you anything more about how the distribution is, whether it's narrow, whether it's spread out, etc. So here, the motivation is to calculate the variance. The variance will tell us how far away from the mean is the variance is the spread of how far the values are from the mean. So if the values are high, that means the distribution is wide and spread out. If the values of variance are low, it is very close to the mean and very centered in the middle. And this is the formula for variance, and all of these expectation, variance, and all of these are derived from the moments of distribution, where you're taking squares and cubes of the variables, like the functions here. I will get into that in a while. But so that is variance. And standard deviation is nothing but square root of variance, because we want the units in the same as the same units as the distribution, because variance squares the values, right? So units are also squared. So we have the general version of expectation, where we take it as, I'm just taking this f of x as x here, for simplicity. So we have this general version where we do p1 x1 k, p2 x2 k, x1k, and so on. Pn, sorry, xnk. So what I want to show here is the first moment of distribution, which is when k equals to 1, is expectation of x, nothing but expected value or mean. When we have k equals to 2, it is the second moment. Expectation of x square. It's not exactly x square, because we try to, variance is not exactly expectation of x square, because we try to center it with respect to mean, right? So we subtract the mean value and square it, but it is derived out of the second moment. So this is variance. In this book, they cover only mean and variance, but we also have third and fourth moments, which is skewness and kurtosis. K is equal to 3. We try to cube it. Skewness is it's x minus mu by sigma, standardization, and then cubed. So skewness tells you about the distribution, whether it's symmetric or whether it's skewed to one side. So suppose we have a distribution like this. This is a symmetric distribution. But if we have a distribution like that, think that's not exactly what I was going for, but more like that. This is right skewed. And then if I have something like that, this is left skewed. It's not symmetric. So when this value is greater than 0, it is positively skewed. That means the tail is towards the right. If it is equals to 0, it is symmetric. And if it is negative, that means it is negatively skewed, tail is towards the left. So this is about skewness. So mean tells you where in the distribution on an average, if you take a random sample, it falls. Variance tells you the spread of the distribution, how far away from the mean the distribution is clustered. And skewness tells you about the tails of the distribution, whether it is skewed to one side or whether it's symmetric. And we have the fourth moment, which is x power 4. But here again, we try to center it with mean and divide it by standard deviation and to the power 4. So here this is called kurtosis. What does kurtosis tell us? So suppose we have two distributions like this, and then this one is like this. It tells us about the thickness of the tails. If the tails are thick, then that means this value is large. If this value is large, then that distribution has thick tails on the ends. If the kurtosis is small, then you have thin tails on the ends of the distribution. When you have thicker tails, right, lots of values are over here of the distribution. But when you have thinner tails, most of the values are here. Why do we need skewness and kurtosis? Because sometimes certain distributions, when you're comparing two distributions, right, they might end up having mean and variance to be the same values. In those cases, if you want to differentiate between them, then you go above the variance by cubing it or taking the fourth order and then trying to distinguish between the two distributions. That's why we need skewness and kurtosis. Next, we have covariance. So covariance tells you the relationship between the distributions, how two random variables are related to each other. So when it comes to covariance, okay. When it comes to covariance, say we have some relationship like this between x and y. And then this one is something like that. This is x and y. And then there is another distribution, which is like this. So covariance tells you the correlation between the two random variables. Over here, we are considering two. So if they are positive, then if both positive, or you can say same sign when you calculate the covariance. By positive, I mean if the covariance is greater than 0. So if the covariance is greater than 0 or the variables having the same sign, then it is positively correlated. This graph does not have any correlation, so no correlation. So anything can happen. You don't know the relationship between X and Y over here. And then here it is different signs. So negative correlation. The formula for covariance is like we already know that. So suppose we have a distribution between we have two variables and their distributions, we can use the formula to calculate the relationship as well. And then we also have something called the correlation coefficient. Correlation coefficient. So why we need this is covariance can assume any value and it doesn't have a limited range. So given a value, say 9 or 17 or 99, we don't know what it actually signifies. So we need a way to measure what value means a positive correlation or how much of a positive correlation between the two. And that's why we try to standardize the covariance. So say we have covariance of f of x and g of y. What we do is we standardize it by its standard deviation. We divide by their respective standard deviations, which is nothing but you can also express it in terms of their variances. So square root of variance of f of x or square root of variance of g of y. So this is the correlation coefficient where we are comparing the variables, and since we've standardized it, now the range is between -1 to 1. So here we can say that if it is a negative -1, it is negatively correlated, the relationship. If it is +1, positive correlation, and if it is 0, no correlation. And then, so that's for correlation coefficient. And then we have something called covariance matrix. So when you have two variables, how does the covariance matrix look like? So you have x, y. I am considering random variables over here, but in the book, they consider functions or probability distributions. It applies similarly. It's just the change of the variables, that's it. So here, when there are two variables, the covariance matrix has the variance of x here, covariance of xy, covariance of xy again, variance of y. So the diagonal elements give the variance of the random variables. And this can be extended to 3 variables as well, where we have the matrix. Here we have x, y, z, x, y, z. And then here in the diagonal, we have variance of x, variance of y, variance of z, covariance of xy, covariance of xc, covariance of yx, covariance of yz, covariance of xc. So this is how we represent the yz. This is how we represent the covariance matrices for the relationship between different variables, right? And this can be extended to many variables. This is also very useful in stats and machine learning when comparing different probability distributions. So that's what is shown here. We talk about correlation and then the covariance matrix and the diagonal elements giving the variance of the variable. So now we move on to probability distributions. Okay, so far any questions, anything anyone wants to discuss? Okay, then I'll move on.
Hey, one small thing. I think in when we calculate the covariance, uh, we we I've seen that we used that 1/n-1, not 1/n, and it says something around the degree of freedom. Is there any intuition behind that? Why we use n-1 while we calculate not n?
Why we calculate with n-1? I have no clue actually.
Okay, yeah, sure. I'll also explore, but I read it somewhere, but a long time back.
I
But at
remember
that,
it being
yeah,
n only, but n-1
correct.
could be something related to
Hmm.
so if I'm thinking of it right, I'm not sure, but something related to the differences between maybe the population and sample, something like that,
Correct,
right? The
correct,
bias with respect to
correct,
that.
correct, correct, correct. Right. Yeah, I also remember that. Yeah.
But
Okay,
I'm
I'll
not
explore.
able to clearly express it. I know it's something related to that, but yeah, I'm not able to clearly
Yeah,
define.
sure. We can explore that and maybe
Yeah.
discuss later. But yeah, that's thank you. Yeah.
Okay, great. Okay, probability distributions. So the book talks about Bernoulli distribution. Bernoulli distribution is a distribution over a single variable that takes the values 0 and 1. And yeah, let's go through one example so that we understand the equations. Okay, so Bernoulli distribution, it gives the probability of the random variable being equal to 1. So let's take an example. When the random variable is number of heads, when we flip a coin, say we flip a coin, which is an experiment. So the probability of x equals to 1 is 0.5. And the probability of x equals to 0 is 0.5. We know this, right? So in a Bernoulli trial, this is called a success because we are looking for the number of heads. This is called a failure. So when we flip a coin, we either have heads or tails. So this is one example. Another example could be if, say, if you're throwing a dice. What is the probability that it lands? It gives 1. And then this can be any other value, right? So the success over here would be 1 landing on phase 1. So the probability of x being 1 will be 1/6. That is our success. And probability of x being any other number will be 5/6. Okay, I don't need to write this all the time. But so here, let's try to generalize it. So x being a random variable, probability of success, where P of X equals to 1 will be P. In the textbook, they've taken phi, but I'm just using P because that's what I'm always used to. So this is the probability of success, and then probability of X equals 0 or failure is 1 minus P. So the definition of Bernoulli distribution will be for X equals to X, probability of, so P of X times 1 minus P of X minus P of, is that right? 1 second. Yeah, right. So yeah, that's what I've written. P of, yeah, instead of phi, I've taken P, but this is the generalization. And let's try an example. I mean, I'll leave this out to you. So suppose we throw a four-sided dice, and we observe that it lands on 2 or not, like whether it lands on 2 or not. Can you tell me what is the probability of landing on 2 when we throw a four-sided die? Like, what is the probability of success here?
One by 4.
Yeah, 1 by 4. So you get the idea, right? Yeah.
Should it be 1 minus P to the power 1 minus X?
That's what I was thinking. Maybe I just copied it wrong. Could you check the textbook and tell me?
Yeah, it is 1 minus X.
Okay. Yeah, that's what I was thinking when I wrote it down, right? Yeah, it is 1 minus 6. I'll correct it in the slide. But yeah, it should be P of X, 1 minus P times 1 minus X. Yeah, only then it makes sense.
Yeah, I mean, like it's 0 or 1. So whichever it is 0, the other one would be 1, like just complementing.
Yeah, correct. Okay, I'll change that later. So that's the Bernoulli distribution. The book also talks about multi-Nolli distribution, where the random variable takes many discrete states, where they write something like, yeah, something like 0, 1, k minus 1. I think this one, can someone explain this? Because this one is, I didn't actually understand quite well from the textbook itself. What happens in this scenario?
It just seems to be, at least to me from what I read, it seems to be like a situation where you can have multiple discrete events, and so it's basically a multinomial distribution, right?
Yeah, but they also talk about some constraint, right? Like something like, I don't remember it now, but they also talk about it being constrained to some value. I was wondering why they do that constraint.
Like there are k states, and the first k minus 1 states, they can be the like 0, 1, but the last state will be decided upon so it will be like 1 minus summation of all probabilities till that state.
Oh, okay. 1 minus summation of all the probabilities.
Of k minus 1 states.
Okay. That makes sense. Okay, great.
I guess this is it, like
Sorry, you were saying something?
Yeah, I think this is it. I am also not sure, but I think this is it.
Yeah, I think even I have to read it a little to understand what they were trying to say, but this is it, yeah. Basically, that's the definition of multinodal. And then we have Gaussian distribution. I'm moving on unless anyone has a question. Okay. So then we have Gaussian distribution. It is also known as normal distribution. It is quite common and popularly used everywhere in science, statistics, machine learning, everywhere. And it's a distribution over real numbers. So here, actually, let's go to the whiteboard. So here, the parameters are mean, which belongs to real numbers, and standard deviation. It's between 0 and infinity. And the distribution looks something like this, where the center coordinate is given by mean, and then the spread is given by the standard deviation. And here the area under the curve is 1. The formula for this is normal distribution of x parameterized by mu and sigma square is equal to 1 by root 2 pi sigma. So this is nothing but a scaling constant. And then e to the power minus 1 by 2 x minus mu square by sigma square. So here, I wanted to talk about, yeah, so here we also, the book talks about the reasons why normal distribution is like most distributions are modeled as normal distribution, and why is it a good choice for being a default distribution. So if you don't know what distribution it is, it's safe to model it as a normal distribution. So one reason being, they say that according to the central limit theorem, many independent variables are approximately normally distributed. So naturally, many variables follow a normal distribution. So it is quite easy to model it as a normal distribution. The second reason that they give is normal distribution encodes maximum amount of uncertainty. So it does not require much prior knowledge inserted. So actually this part I don't understand. What does it mean when it says encodes max amount of uncertainty? I mean, can anyone explain that to me?
Can you repeat once, like what is the line?
So they talk about why normal distribution is a good approximation for many random variables, and they say that they say that normal distribution encodes a maximum amount of uncertainty over real numbers. I was just wondering what that is. Maybe I'll try to share my screen. 1 second.
Okay.
Can you see my screen?
Yes.
Okay, so this part, the second part, where they talk about out of all possible probability distributions, it encodes the maximum amount of uncertainty and least amount of prior knowledge is required to be inserted into the system. I mean, this particular part I did not get it.
Could it be the area under the curve?
Like
Maybe not.
area would be one for
Mm.
all the distributions, right? And I mean, what they're trying to say is it encodes maximum amount of uncertainty.
Yeah. Like, does anyone understand this,
Mhm.
or maybe we can come back to it later?
I took it to mean like, if you look at a person that is specifically, for some kind of distribution, right? Or if you look at, say, Bernoulli in the previous one, that's only for binary outcomes, right? Discrete binary outcomes. So
Oh, yeah.
there is some amount of knowledge. You're saying that, okay, I know about this application, and it only has two outcomes, or I know about this application and it only deals with, I think time, the intervals, right? So,
Mm.
and so those are like prior knowledge you are encoding. But with normal, you are saying that, I don't know anything. Most likely it's a normal because everything is normal, right? So that is
Okay.
what I took it to mean. Yes.
Okay. Okay. Yeah, I think we can think of it like that because it is over a continuous range, right? So any distribution can be modeled as the Gaussian distribution. So okay, here in the textbook, what they do is it's parameterized by variance, right? So what they say is variance has to be divided and squared. So sometimes in computation, it's difficult to do that. Why don't we replace it with precision? Precision is beta. So wherever there's sigma square, there's 1 by sigma square, it's replaced by beta. That's all there is to it. And to the point where they talk about normal distribution is quite common. Some of the applications where you can model them as a normal distribution is maybe heights of people, weights of people, any continuous range of values, right? You can model them as normal distribution. And even in machine learning, many variables follow more normal distribution. And then, like we already saw the graph of the distribution. So we have the maximum at x equals to mu, and then we have these inflection points at mu plus or minus sigma. Here, I actually want to talk about something else. So when we are referring to normal distribution, right, we have this rule called 68, 95, 99.7 rule, where we talk about data being within 1 standard deviation of the mean, or 2 standard deviations of the mean, or 3 standard deviations of the mean when we talk about data within normal distribution. So nu plus or minus sigma, the data that's present within this range is 68%. So 68% of data is present within mu plus or minus sigma. And then you have plus 2 sigma minus 2 sigma. 95% of data is within this range. And then minus 3 sigma plus 3 sigma. So plus or minus 3 sigma. 99.7% of data lies within this range. This is one thing that we come across when we talk about uh, it being within 1 standard deviation or 2 standard deviations of the mean. What we mean is what percentage of data is within that range. And then we have multivariate Gaussian distribution. So that was for a single variable, right? Here it is for 2 or more variables. So here the standard deviation becomes the covariance matrix. And actually, I tried to look at this derivation, and yeah, it's a little, it's not complicated, but it's a little mathy. So I think I won't be able to reproduce it here, but I'll be sending out like a note of the derivation so that everyone can refer to it, like how you can derive it for two variables and how it can extend to many different variables. Here also, the covariance matrix is replaced by the precision matrix. It's the same thing. Covariance matrix is difficult to um, like compute, and then you can replace it by the precision matrix, and computation of the inverse of covariance is difficult, right? So instead replace it with the precision matrix and the computation becomes easier. Next we have exponential and Laplace distributions. So the exponential distribution talks about if events happen continuously and independently with respect to each other, how much time it takes for them to happen. And the distribution looks something like this. So it's an exponential distribution, and lambda is nothing but the rate at which the event is happening. So these are three different events happening, and then we can compare them based on their exponential distributions. It basically tells the time until which an event happens for each of these. And then we have Laplace distribution. Laplace distribution is nothing but, it's called a double, so as it's written here, right? It's called a double exponential distribution. So basically you can think of two exponential distributions along this line. And so it is the difference between independent identically distributed exponential random variables, and this gives the Laplace distribution. And if mu is equal to 0 and b is equal to 1, it's nothing but so it's nothing but a positive half. So the positive part is nothing but the exponential distribution is what they talk about. Yeah, this yeah, I mean, this I not so clear with, so this is how much I know about these two distributions. And then we have
I
sorry.
was wondering if there was a real life, example of what kind of distributions would be a Laplace distribution, would be, modeled by a Laplace.
I think signal processing.
Okay.
Yeah,
Probably.
I remember it being seen in signal processing maybe.
But
Different.
one question I had, like, since we are using absolute function in the Laplace distribution, it it is not differentiable at x equals to 0, right? I mean x equals to mu. So like, then does it cause problems in calculations later on in different
At x equals to mu.
x
Okay.
equals to mu? Yeah, it's not differentiable.
Yeah. So in those places, sometimes we take it as I'm talking. Okay, for this maybe not, but for similar cases, right? In those cases when it's not differentiable, we usually take it as 0, because even for some functions in machine learning, when we are differentiating, it is if it is a sharp point, we usually consider it as 0, and then it we usually consider it as 0, or we usually consider a small value, and then we back propagate that value. So I think there is some kind of
Okay.
a solution to that, but
Okay.
I'm not sure. It depends on the
Yeah, I think,
application, I guess.
yeah, right. So I think it's similar to ReLU as well.
ReLU, right?
It's
Yeah.
a continuous function, but not differentiable at zero. So we just, you know, consider that as zero.
Yeah, I was talking about ReLU only. ReLU is not differentiable. Uh, let's okay.
Yeah, it
So
has
if
a
you look
sharp
at ReLU, right,
point.
it has a sharp point here at 0. So here it's not differentiable. So that's why we have different variants of ReLU where we make it a smoother version, like soft plus that we come across. Sorry. Oh,
Okay.
that's a video.
So like,
Sorry. Sorry, someone
Yeah,
was talking.
yeah,
yeah,
yes.
yeah. In fact, when I first saw ReLU, and then there are Pelu, Selu, Gelu. I mean, I initially thought that the people are just mimicking, but actually found these are the activation functions actually available. But when it comes to uh, performance and other things, Relu is still far better, and that's why it has been used generally by mass. But yeah, as you said, just to mitigate that smoothness. They came up with different functions, but still today, Rail is more popular with respect to others. But that is, this differentiability problem at a certain point, most of the time it is at zero, is there in most of the cases.
Yeah. So even with ReLU, initially when you pass something through this activation function, right? Only if it's positive, you will have something, a value. Otherwise, it's 0. So this is one of the causes of those vanishing gradients also, right? Where like if ReLU is not activated, you don't get back any signal. So for this, they try like different variants of ReLU have been tried, where instead of making it negative, try to make it like some signal, but not entirely. Sorry, instead of making it 0, let's back propagate a small signal back, and different versions, like there is something called swish also, like different activation functions came about after that, but yeah, ReLU is only used nowadays. Other activation functions are not that prominent. So I think, yeah, when it is not differentiable at that point, maybe there is some
You can also take like 0 plus epsilon, where epsilon is like a very small quantity, and that'll have a number, right? That'll have a value. And
sorry,
so
come again.
you can differentiate. So if x is 0, so and it cannot be differentiated at that point because it's non-contiguous, you could add
Right.
a very small number, 0 plus epsilon,
Huh.
and that would be differentiable.
Right.
Right. So
Correct.
I think that's the trick they use for ReLU.
Yeah. Okay, so that's Laplace, and then there is direct delta function and the empirical distribution. So let's see. Yeah, so the direct delta function is this impulse function, right? Where it is it has a signal at 0, but everywhere else there's no signal. So it still has an area of 1. And this function is used for approximating the empirical distribution, where empirical. Yeah, this function is used for the empirical distribution where they say that it puts a probability mass on each of the different points of the training data. So basically, is it that okay? This also I wasn't that clear when I was reading. So basically, does it say that it uses the direct function for each of the samples, like to combine each of the samples through the summation, and that's how the probability distribution is created? I'm sorry if I'm not making sense.
Could it be like a continuous approximation of the multinull?
Yeah, that's what they say. Yeah,
Right. Okay.
it could be. Yeah, in a discrete case, it is nothing but a continuous approximation. Hmm. Yeah, I mean, the second half of the chapter, like even I had a few questions and doubts on my own side. So next we have mixture of distributions. So in this, what they talk about is trying to combine different distributions to create a richer distribution. Basically, an example that they give is the Gaussian distribution, where there are, I mean, in this example, they show three different samples or components where this one has isometric covariance, meaning that it's the same in all directions. Over here, this is a diagonal covariance, where in one direction, the covariance can be controlled, the variance can be controlled. And this one is a full rank covariance, where variance can be separately controlled along any direction. And for a Gaussian mixture model, each of the components is are Gaussian, and they are parameterized separately by the mean and covariance. And they also talk about these components sometimes sharing covariances. And if it's a single component, they are usually having isotropic covariance, like this component. So that's what they talk about. And they also talk about Gaussian being a universal approximator. So any density function can be approximated with the Gaussian mixture model with enough number of components. That's what they talk about over here, mixture of distribution. I think that's for distributions. Any questions, any discussion over here before we move on? Okay, so next we go to the functions, some common functions. Logistic sigmoid, I think all of us know about this function. So the curve is this way, where it saturates towards the positive and negative ends. And this is the formula. Logistic sigmoid is used a lot in machine learning. It's one of the activation functions. And it produces the parameter phi of a Bernoulli distribution because its range falls within the range of phi. Then we have soft plus. So here, soft plus is a smoothened version of max of 0, comma x. This max of 0, comma x is nothing but a ReLU function, right? So this is, instead of being a sharp rise at 0, it's smoothened out at that point. And yeah, it is used for producing the sigma parameter of a normal distribution. So this is a property. And they also introduce sigma inverse of x, which is the logit, and they talk about it not being used in machine learning, so it's not included here. Yeah, and then towards the end, they have the Bayes rule. Bayes rule is finding the probability of x given y when we already know p of y given x and p of x. Even if we don't know p of x, we can actually find it using, one second. So we can find it using the summation over x, p of y given x times x. So we need not have the knowledge of p of y. And then, so this Bayes rule is popularly used in spam detection example. So I know Bayes rule in terms of another way also. Let me. So in terms of events, I know it in terms of set theory where P of A given B is P of A intersection B by P of B. This is how I know. And then actually this formula is further decomposed into something like this: probability of A times probability of B by A by probability of A times probability of B given A plus probability of A complement times probability of B given A complement.
Okay.
This is one form of Bayes Bayes theorem. But here they're talking in terms of distributions. That's the difference. And we can derive this from conditional probability as well.
Yeah, you can also derive from your version, right? It's
Yeah.
also derivable. The
Yeah.
bottom becomes P of P.
Yeah, this becomes P of P, right? And next we go to the information theory part of it. So here they define information theory. Basically, it quantifies the amount of information present in a signal. Initially, it originated from radio transmission to study communications, to identify what is the optimal code that needs to be designed and what is the length of the message that is expected to be received. But here they use it to characterize probability distributions and to understand the differences and similarities between different distributions. And yeah, the intuition here is say we have an unlikely event that has occurred. They say that having an unlikely event that has occurred is more informative than a likely event. And then the example here that is given is the sun rose this morning. It's not that informative and it's not needed. It's not essential information to be sent. But something like there was a solar eclipse this morning is actually very informative, and that is something that is important to be sent as a message. And they define this intuition formally, saying that events that are likely to happen have low information. Events that are guaranteed to happen, that you know they will happen, have no information, are supposed to have no information. And less likely events have a higher information content. And if there are independent events that are happening, they have additive information. Suppose you're tossing a coin twice, then that is additive information of, sorry, suppose you're tossing a coin and it lands on heads twice. So two times you get heads. That means the information is added of the two heads instead of just having a coin tossed and you just have one head. And that's only one information. And then we have these definitions, definition of information, which is the amount of content, information content present in the random variable's outcome, which is I of x minus log of px. And then we have entropy, the amount of uncertainty in the distribution. Or it can also be the how much amount to expect in the information of the event, which is given by the expectation of the log of p of x and the KL divergence. KL divergence is the it is used to measure differences between distributions. How different are two probability distributions? So that is given by the expectation of log of px minus log of qx. So an example of Shannon entropy is given here for a Bernoulli variable. So they say that over here at the probability distribution where the random variable, sorry, over here when it is 0, when the probability distribution is 0, then the entropy is also 0. The distribution is nearly deterministic at this point, and that's why the entropy is low. And over here, when the probability is 1, even here it is nearly deterministic and entropy is 0. But over here it's high. So the entropy is maximal because the probability over here is 0.5 for a Bernoulli variable. And the distribution is uniform. So this is an example to show how Shannon entropy is. And then we come to the properties of KL divergence. So KL divergence is 0 if both the distributions are same in terms of the discrete case. And in terms of continuous case, we coin a term called almost everywhere. It has to be same almost everywhere along the two distributions. And one important property of this is they're asymmetric. So the KL divergence of P and Q is not equal, actually, sorry, it should not, sorry. Here, this is wrong. It should be not equal to, I'll change that later. So for two distributions, they are not equal. And there is this diagram where they show the asymmetry. Actually, this one, can someone explain this to me? How they are showing the asymmetry over here?
Yeah, it wasn't clear to me too. So
Yeah. Okay, then we'll just take it as homework and then read up more on this. Okay, great. Moving on to the next, structured probabilities. They talk about machine learning having probability distributions over many random variables, and most of the times they don't have direct interactions between these variables. So you can factorize them as different probabilities multiplying each other. And these factorizations reduce the computation cost and number of parameters as well. And the representation of these factorizations can be done in terms of a graph with vertices and edges representing those random variables as vertices and the distributions as the edges. To give you an example, they show they are categorized as directed models and undirected models. In directed models, the edges are directed from one vertex to another. And the factorizations in this case are conditional probabilities. So from this example, A is connected to B, A is connected to C, B is connected to C, B is connected to D, and C is connected to E, right? So to multiply these factors for A, since it's not being influenced by any other variable, it is just P of A. For B, it is influenced by A, so it's P of B given A. For C, it is influenced by A and B, so it's P of C given A comma B. For D, it's influenced by B, so it's D given B. And for E, it's influenced by C. So this is how you can multiply the different probabilities and the conditional probabilities. For undirected models, there are no directed edges. They're just connected by the edges. So any connection with the edges is known as a click. So ABC is a click, CE can be a click, and BD can be a click. So when you take that into consideration, here the factorizations are represented as a set of functions. So the phi is like a factor, and phi is a factor of ABC because they are one click. P2 is a factor of BD because that's one click because they're connected together. And CE, P3 of CE is another factor. So, and 1 over C is just like a normalizing constant. So basically they're trying to show that probabilities and conditional probabilities can be factorized and they can be represented in terms of graphs because it makes it easier to understand and visualize these random variables and their associations with each other. I was watching one reading group lecture, and at that time they were also talking about how they wanted to use these graphs as inputs to the neural network at that time, and they weren't successful. But today we see that we have graph neural networks as well, right? Where they take graphs as inputs and they try to do some function with them. So it's also interesting to read this book to compare the advances between then and now. At that time, they hadn't they were having too many complications with graphs as inputs, and they were unsuccessful. But today we do have graph neural networks, and we see that it has been quite useful in many areas as well. So that's it. I think we're done with the chapter. Any questions so far? Uh,
For the structured graph models, at
mhm.
least the directed ones, the impression I get is that it simplifies calculations if you bring in external knowledge, right? So I did, like ordinarily, if you did not know of any relations between, A, B, C, and D, A, B, C, D, and E, you would do the typical, the chain rule kind of thing, right? Where
Right.
you would, but now that you know that E, for instance, is not directly connected with A, you can break it up differently, right? So that's kind of also the intuition behind Bayesian networks, right? Where you can
Right,
set up
right.
your thing and you can calculate things and you can say that, if I change something here in one of the nodes, how does the change affect this other node at the end
Other
of the,
nodes.
so yeah.
Yes, actually, the structured probabilities, I forgot to mention. Thank you for reminding. I was meaning to talk about this as well. This translates into Bayesian networks and like probabilities uh, in that area. So I think that's what they were going for when they brought this up as a topic in the book as well.
Like why are we multiplying here all the probabilities?
Because that is what they were talking about, factorizing them into product of the probabilities.
It's the chain rule, but with the additional constraints that you have here. So you're applying the chain rule along these relationship edges, basically.
So like what is the interpretation of like the left part of the equation? What is that what is the meaning of the probability? Like
This is the joint probability of the whole thing, right?
okay.
Of all these things
Yeah.
happening. And so if you want all these things to happen, for anything to happen, A must happen, right? So therefore PA. And for B to happen, A must have happened already, because that's the only thing that, therefore B given A, right? And so on, all the way down
Okay.
to E given,
Okay. Yeah. Yeah.
Yeah.
So there was like there is just to on this point. I was just checking few problems on this particular topic of conditional probability. I'll add that in the Google Drive. I was just checking last night. So there are uh, there are few problems which are very tricky to solve, but when you put it in this graph or a tree structure, it becomes very easy. So one of the problem that I was reading is let's say you have a dice and you are rolling it continuously until you get two heads, consecutive heads. It sounds very simple, but when you start doing it, it's very difficult. It's a recursive expectation. You have to use that. But when you do it through graph, it becomes very simple when you try to formulate that. I'll share those problems, and maybe next we are done with this chapter.
Yeah.
We can solve that. It's very good. Like I learned a lot when we pick any problem where recursive nature is there in the problem itself.
Mm.
We can probably do a session only for question answers, like in the next session. We can just conduct question answers for all the chapters, linear algebra,
Until
and
now, right? Yeah.
Until now, yeah, that's a good idea.
we can we include fourth chapter as well for that?
Sure, yeah.
So like if that is the case, like we can. So I had a concept in mind, like if just I want to know how do you feel about it. Like we can contribute, each of us can contribute some questions. Let us say like 4 to 5 questions, and we can pool those questions and conduct them in the discuss them in the next session.
Yeah,
Yeah, sounds good.
Right?
So next session will be about what is that chapter? Numerical computation, right? Would it take the whole 2 hours, or would it be 1 hour of that, and then the second half we'll be trying to.
I was thinking like, what if I conduct it in a like question answer format, like whatever we have learned from the chapter, uh, I can like present some questions,
I
or even
see.
you can present.
Got it. Yeah, we could do that.
Yeah. So we can pool the questions also. Like if you guys have questions, and you can just present that at that time, like instead of like giving them right now. Uh, I think next chapter has some concepts are if there are doubts in some of the concepts, can discuss them also. But we can devote mainly for question answers.
So, chapter 4, we are basically including or skipping? What are we doing?
So I was thinking in like conducting the session, chapter 4 in a question answer format, rather
Okay,
than
I see.
yeah
So, flip the class basically. So, everybody reads chapter 4 and then comes up with questions, and then we just discuss the questions, right?
yeah
Okay.
yes. So
Yeah.
like any other suggestions
Yeah,
you
I will
have?
miss the class next 2 weeks. So, but I
Okay.
can definitely submit questions. And if you record it, I will listen to your answers.
Yeah, sure.
Right. Yeah.
So did you say questions submission about chapter 4 or until chapter 4?
Everything. We
Including
can
chapter 4. Yeah.
Including
including
chapter.
chapter 4.
Okay.
Yes.
so we
Yeah.
completed part one of the book.
Yeah.
Such a milestone in my life.
Yeah.
Yeah, but like
So
until we haven't completed it, will
Yeah,
be
machine learning
completed
basics is there still. Yeah.
Oh,
it is
okay.
a big
Yeah.
chapter.
Yeah.
Yeah, I started to celebrate. Okay, yeah.
You've not reached the milestone yet.
Yeah.
But yeah, we're close.
Yeah, thanks,
And
Sachin. I
Reading this
think
book has introduced more questions, like more doubts in my mind about many
yeah,
different.
actually, all the doubts, right? We can store them in somewhere, and even I'm like trying to. I had some doubts in linear algebra. I'm trying to prove them
Correct.
simultaneously
Yeah.
as I go on.
Even in linear algebra, there were certain places where I wanted to go through it in detail and have. So basically, what I wanted with this sorry, with this reading, right? As I go through the chapters, like whatever equations were there or whatever questions I had, I wanted it to be clear after every chapter reading, but looks like I wasn't doing that consistently. So I have to sit and do that.
Yeah, I
yeah,
think if we conduct a question answer session, and that can be a brainstorming session as well, like for everyone.
Right.
yeah. So I think for me as well as just as Ratna you mentioned, for me before even start any chapter, I really get scared. And to be very frank, it's like few of the notations that they use, like you use P, right? And that's what I also, I mean, most of the people
Ah,
have used. That phi itself make a difference when you start reading
exactly.
that.
When I
The
saw that
psychological
phi,
thing, yeah,
sorry, when I saw that phi, I couldn't recognize the equation. I was wondering,
right,
what is this? And then I referred, I have my notes with me. So then I referred to my notes and I was, oh, P. Okay, this makes more sense. Even for the random variable, right? They have a small x in different italics and different notation. But I usually prefer random variable to be written as capital X and the values it takes as small x, because while writing it on piece of paper also it's easier to write it that
yeah.
way. So I, because of the notation changes, right, which I'm not used to, uh it feels like a different equation, or it feels like something new that you haven't seen before.
Yeah, it's not, this book is not at least to me, it's not an easy read. Even if
It's not.
some certain background, I would say not certain, a good amount of background you should have before even start this book. And just to understand the simple thing, you have to read. I mean, at least for me, I'm talking about myself. I have to read other literatures to get the exact. Thing from here, and if we understand that and then we read this book, we actually get the value out of it, because there is a lot of times I've realized that the author has written something in a very crisp, concise way in 2 lines, which is very difficult to summarize when you read some from other book. But it basically the gist, at least the initial 3 4 chapters, which are kind of a primer for from the next part onwards, maybe it will be more
Right.
detailed. But this is certainly a hard book to go through.
Yeah, I found it very difficult, especially for this probability chapter, right? Which is, I felt it took me a long time to actually go through reading the chapter. And if you've seen my notes, everywhere I've written, I don't understand this. This is a doubt for me. So everywhere I've written places where I had doubts, and then after one iteration, I went back to the start and then started clearing my doubts by looking for resources online and trying to find extra information that's not
Yeah,
available in the book.
right. So, Amit, would you like us to pick up different chapters for 5 6 questions for each of us, or now, so that we know we can pick that particular area and pick up the questions, or it can be open for.
Let it be open. I think
Okay.
if you
Yeah, let
find
it be
something
open.
good, yeah.
I mean, if you want to, so you can also divide the. So there are, I think, 3 chapters: linear algebra, probability, and numerical computation. So you can divide like equally also, as you wish.
Okay. Okay. Yeah, yeah, sure. Yeah, yeah. I also
So
have no interest. I don't have guts to pick one area, but I just thought to check, like, if there
So
is
no,
something.
let's keep it open because
Yeah.
Yeah,
like
if you
someone,
have
as you
like really
said,
good questions
yeah,
in a particular topic, you can
Sure.
take more questions also.
right. And Suman,
Sure.
as you said, you came across that good question, which was recursive in nature, right? But say you didn't pick linear algebra for your question,
Yeah. We'll miss that question.
you'll
Right.
miss out on
Yeah.
that question. So, I
Yeah.
mean, let's not be so specific about it.
Correct. Yeah. Okay.
We can perhaps keep a timer on time, like time constraint. Like if I think we 4 are there, perhaps
5 of
in the
us.
next session. I think Sujit is not there,
Yeah.
Oh, okay.
so we can like divide half an hour for each person's questions, or
Yeah.
we can just discuss it chapter wise because it will be otherwise a mix of everything.
Let's do chapter wise. Let's start
Let's
from.
do it chapter wise.
Yeah. Chapter wise. Yeah.
I
Great.
think I didn't understand exactly, but you plan to ask the questions before or come with the question and the answer?
No,
Because
like
I was no, go on.
you can keep the questions to yourself and ask them in the session itself.
Because I was wondering if I think that would be more maybe more productive if you release the question before, because for
Okay.
you arrive at the session and then you have no time to look for answers. So except
Okay.
if somebody knows already. I don't know, but if not, then we
Yeah.
look at the question and we say, oh, okay, I don't know.
Yeah, maybe drop them in the Slack.
Yeah.
So,
Yeah, we can do that. Yes, we can make the like question bank beforehand itself,
right.
so that everyone gets time to work on it during the week. So, like I have made a Google Doc for questions. So perhaps you can add the questions there.
Yeah, that's a good idea.
Yeah.
If you can share the link, then or if it's already there in the Slack, then it's fine.
Yeah, it's there. It's there in the Slack, but
Okay.
I can add it in the description. And I think I have. I think I have just given the commentator access right now.
Or if you want to keep it that way, create another Google Doc with like shared access.
Updated.
Everybody can edit, and then we can
Yeah.
use that. And then you fold in whatever dedoping or with answers and all, right, in the Google Doc for later.
Yeah, sure. Yeah, I can do that. Okay then. So we can, I think, end this session today.
Okay. Right.
Yeah.
Sure. Thanks, everyone. Yeah. Have a good one.
Thank you. Yeah.
Thanks.
This is very,
Thank you.
yes.
Bye.
Enjoy
Take
the
care.
weekend.
Right. Thanks.
Have a good weekend.